Hello, dear participants and guests of the Information Technology and Nanotechnology Conference, ITNT 2021. My name is Nikita Andriyanov. I am Associate Professor at the Department of Data Analysis and Machine Learning at the Financial University under the government of the Russian Federation. And my video presentation will continue to be devoted to the most relevant topics of recent months. I will try to analyze the impact of restrictive measures on the spread of disease using the example of COVID-19. So let's start. One of the most discussed topics in 2020 was the topic of COVID-19. The Oxford English Dictionary even honored the word coronavirus with the word of the year. A special surge in the activity of publications and mentions on this topic, of course, occurred in the spring of 2020. Nevertheless, even now the conference is being held in a mixed mode, including due to the pandemic. And in the spring of 2020, many countries began to impose restrictions to combat the spread of the virus. Someone supported it, someone was dissatisfied, somewhere we still see protests against restrictive measures today. But our research is trying to find a relationship between the measures applied and the number of new infections and other indicators. It should be noted that the period for preparing the abstracts fell at the end of 2020 and the data analyzed at that time. However, with the advent of the coronavirus, methods of dealing with it began to appear. In many states, the authorities have introduced and continue to impose various restrictive measures. Unfortunately, assessing the effectiveness of the measures taken is a complex task associated with the need to apply data mining methods. Despite their capabilities, questions arise about fault compliance with measures, partial violations, and etc. In addition, other factors can also influence the spread of infection. Nevertheless, in a simplified model, knowing that date when a particular measure was taken, it is possible to indirectly estimate its impact on the number of new cases detected over time or the percentage of sick and healthy people. This report will consider such characteristics for two states: Russian Federation, France, and United States of America. The model of interaction between neighboring large and small cities should be especially highlighted, when usually many people from a small city go to work in a big one and spend a lot of time there, and then return in small city. However, in a pandemic, such movements obviously only accelerate the spread of the disease. This raises the problem of assessing the spread of COVID-19 in the context of the introduction of closed borders between cities. Such a limitation radically changes the migration processes and accordingly the process of the spread of pandemic. Simulation modeling can be used to assess these changes. We use the data from different sources. Let's speak about the initial data. The analyzed data was obtained from the Coronavirus Tracker API repository. This API provides access to three sources of information at once, such as, for example, Conference of State Bank Supervisors and the New York Times. However, this report analyzed information received from the Johns Hopkins University Center for System Science and Engineering. Since this source has proven itself well during the first wave of COVID-19, it is worth noting that this source provides fairly complete data for the vast majority of countries in the world. Indeed, Johns Hopkins University collects and processes data from more than 100 different sources, including internet resources of different states, such as stopcoronavirus.rf website, which is the official source of data on the COVID-19 in the Russian Federation. We also use the Oxford COVID-19 Government Response Tracker, dataset from the Oxford repository. It provides fairly complete information about the policies of various states related to the introduction of restrictive measures. The most important indicator is the Government Response Index, which describes the government's response. The total response of the state is calculated as the sum of responses in various areas. The slide lists the criteria of governments to act. You can see them in more detail in the text of the article. I can highlight stay home criterion, masks criterion, and others. Initial analysis was performed on the original dataset as of November 25 in 2020. Let's consider the number of detected infections with coronavirus in different countries by day, in the figure on the left. This graph does not provide us with any useful information in terms of studying and analyzing the spread of coronavirus infection. Let's transform the data displayed on this graph. Let's build a graph of the incidence, the number of infections from the population, in the figure on the right. Comparing the top 9 countries in terms of incidence with the top 9 countries in the terms of number of cases, we note that no country is present in both lists. Thus, we can conclude that we can get more benefit from the analysis of the incidence graph. What about geography? It is also worth noting the geographical position of the countries from the top 9 in terms of incidence presented on the slide. In general, what is interesting, if we compare the proportion of the infected population, then we see that the countries were mainly scattered across Europe and Asia. Let us consider the statistics of new cases of diseases in a similar way. Analyzing the figure on the left, we can say that the increase in diseases does not differ much across countries. Only Luxembourg, San Marino, and Andorra can be distinguished, in which the indicator reached the highest values on some days. These countries are present in the top 9 in terms of the percentage of infections from the population of countries. But it is important to understand that the population in these countries is quite small, which can lead to an error in the analysis. The indicator of the number of active diseases shows a completely different picture. See figure on the right. Consider the mortality rate of the population from coronavirus infection. The number of deaths from the number of diseases, figure on the left. We see that even at the highest mortality rates, the indicator does not reach 10%, with the exception of the extreme indicator in Yemen. It is 28%. Let's consider how things are going with the percentage of recoveries. To begin with it, let's take a look at the recovery graph for the 25 largest countries by population, figure on the right. The graph clearly shows the decline in the recovery rate in France. Let us consider this graph in more detail. The recovery rate began to decline significantly starting on June 15th, and there is an actual explanation for this. According to information on restrictions in connection with the coronavirus infection started from June 15, the French government has lifted restrictions on border crossing for residents of Europe. And since November 6, there has been an increase in this indicator since lockdown was reintroduced in France. This raises the interesting challenge of assessing the impact of governments on the rate of spread and containment of a pandemic. Consider the dependence of the percentage of recoveries on the total measures taken by the French government. The resulting relationship can be analyzed from the picture on the slide. Analyzing the infection points, it can be seen that with a slight delay, tightening measures leads to an increase in the percentage of recoveries and vice versa. It should be noted that the y-axis represents the percentage, and for measures, the 100% index corresponds to the setting of all types of restrictions. Let's pay attention to the part of the graph numbered 1, Starting from March 17th, you can see that the rate of measures taken by the French government began to rise sharply. Let's pay attention to the graph of recovery in this period of time. A significant increase in the percentage of recoveries from the total number of cases of infection began. Next, consider part of the graph under number 2. On June 21, 22, the state response rate decreased from 72 to 59%, which with a small lag led to a gradual decrease in patient recovery. Part of the graph at number 3 shows that after the introduction of additional measures on October 29, 30, a slight increase in the recovery rate began. And what about Russia? Let us test the hypothesis about the influence of the state response on the recovery rate in Russia. Let's pay attention to the growth of the state reaction index at the point of the graph number 1. Due to the increase in the state reaction, there is an increase in the recovery rate of those infected with coronavirus infection. And point 2 on graph 2, it can be seen that the state's response was reduced, which with a small lag. Let's do a drop in the recovery rate at point 3. At point 4, the government's response increased again, and already at point 5, an increase in the recovery rate can be observed. So we should see situation in the United States of America. Consider similar data for them. The dependence of the percentage of recoveries on the measures taken are presented on the slide. At point 1, one can observe a rapid increase in the state's response to the spread of coronavirus infection. Further, the state's response indicator remains almost unchanged, with the exception of an increase in this indicator in November. Point 2, which is caused by attempts to stabilize the situation after the fall in the recovery rate that occurred during the recent presidential elections in this country. And the second part of the report are devoted to migration processes and spreading of infection. We also investigated the migration model with open and closed borders in the analogic simulation environment. There are two cities, large and small. Migration process can be described by a system of differential equations of the form 1. Here, S1 and S2 are values characterizing the population at a certain point in time in the first and second cities respectively. Coefficients K1 and K2 calculated by the formula 2, where total 1 and total 2 are the total population of cities 1 and 2 at a certain point in time respectively, and coefficients M1 and M2 are migration flow in cities 1 and 2 at a certain point in time. They characterize the intensity of migration. We use any logic. Let total 1 be 500,000 and it will be big city. Total 2 will be 80,000 and it will be small city. And coefficients of migrations M1 and M2 will be 0.01. By modifying the ideas inherent in formulas 1 and 2, we come to a system in which there are also groups of sick people, their transitions to the state of the recovered, and the death. The diagram of the process in any logic is shown in the figure on the slide. The flows of transitions between states are specified by probability coefficients. We set them in accordance with system 3. And results. Using such a model, a situation was simulated when the borders between cities are open. The slide shows the simulation results. We see a peak increase in diseases of about 150 days in both cities. And we also simulate another situation. The imitation of the spread of the disease with closed borders shows that an epidemic was avoided in the second city, small city, and the analysis of the graphs presented shows that closing borders is an effective measure in combating the spread of the virus. What about conclusions? So we collected and analyzed data on the impact of restrictive measures on the stabilization of the situation with the coronavirus. The analysis carried out on the example of Russia, France, and the United States of America showed that the relationship between the degree of severity of the measures taken and the percentage of recovery in the state is about 65%. Finally, a simulation assessment of the effectiveness of border closures has shown that such tough measures can significantly reduce the rate of spread of infection. Thank you for your attention. This concludes my report. Be healthy. Goodbye.